Today I'm going to show you one nice identity which is related to Riemann zeta-function. It says that the value of the series which Riemann zeta-function is generated by in one half could be actually permuted to anything we want. Uh, it's inspired by one video by Arik Kanani. Actually, there he suggests to subtract those series in the point of one half, well, actually on the critical line, and claims that it should be zero as bolt minus bolt equals zero. But it's not that simple. It would not be mathematics if it was that simple. So here I'm going to introduce you the method to rearrange this series for any real x to converge to any real x. So what shall we use here is this identity. Actually, it is the main of our identity, and from this we can immediately jump here. So what is going on here? Here we just choose those scary term, just to ensure our indices to be well defined. How it works? I shall bring more explanations by the link in the description. So how it works? Actually, we can remember that the definition of the sum of the series is just a limit of partial sums. So if we substitute this infinity by limiting to L or something, we would obtain this identity. So since those terms would just click like a Lego. So our goal would be this. Since if we prove this, we've built our permutation. So if it is not the numerical proof of his method not being methoded, I don't know what would be the numerical proof. Before we start, I want to say a few words about what would be happening to this channel. Actually, as you may remember, I was studying the universality property of Riemann function. Actually, which led me to, as I think, the disproof of Riemann hypothesis. Actually, you can see it by the link in the description. It is a long lecture on this. So what shall I be doing next? Actually, I had another approach to attacking this problem and proving this extended universality for Riemann function. And if I'm correct with this another approach, it opens a lot of avenues for further research. Like it may lead us to finding the universal function which is expressed in elementaries, which would be a huge step for our machine learning abilities. And actually, I want to study the generalization of universality property, not to a disk in one complex dimension, but to polydisk in C to the power of n or something like that. So if you want to support my research, and if you want to see my videos more often, and what am I actually doing, you can support this channel by PayPal. Actually, I would appreciate literally any donation, as if I'm correct, it gets us closer to the new era of machine learning and new era of our mathematics completely. So, why am I so confident about this? It has been it has been almost 4 months of considering by actor mathematica since last revision. So I think that if they could find some fatal bugs in my proof, um, they would reject it far sooner. What do you think? So if you want or if you agree with me or disagree, please write this in the comments. And now, well, I think I've said everything. I've said everything I wanted to say. Mm. Yeah. So uh, and uh, before we start, please let us make the world a better place together. I'm also open to communication, so please, if you've got any question, don't be confused to text me. I shall leave my email in the description as well. So now is everything. So let's get started. So our main tool would be this beautiful identity. So actually, this identity is first met by me in the video of, by Arik Kanani, and it is quite a beautiful asymptotic and kind of beautiful way to get the analytical continuation of Riemann's zeta function to the critical strip. So how it works? First of all, we need to verify that each term of those is holomorphic everywhere for real parts of S greater than zero, except one. Actually, as the Riemann zeta function has got a simple pole in one. And what do we have here? Here we have for some finite sum of exponents, which is actually homomorphic as an entire function. And here we've got um, we've got this term, which is an exponent divided by linear function. Actually, it is everything is all right with it, since we've got an exponent here, which is an entire function, and this for a fraction turns to infinity only at the point where real part of s is equal to 1. But but it is already a pole of Riemann zeta function, and you can see that in this representation it is it is with a it is a simple pole in the point 1 with the residue being equal to 1. And here we've got an absolutely convergent integral for any real for any s from this domain, and in the neighborhood of any s, this integral is being absolutely convergent. Thus, it is being uniformly convergent. And here we note that it is in fact the holomorphic function with respect to s, as it is the integral of holomorphic functions with respect to x. So what are we left to do to prove that that is indeed the analytic continuation for a Riemann function? Now it is enough for us to show that it coincides with the Riemann zeta function on the domain where real part of S is greater than 1 by identity theorem, since a Riemann zeta function is holomorphic is holomorphic everywhere, but not in the point one. And second, the domain where real part of S is greater than one consists of accumulation points, and thus we are enough to show that it can size. So to do that, let's look at this guy right here. We shall just compute it. Assuming that the real part of our S is strictly greater than one. So what it would be? First of all, let us rewrite this guy right here. X minus 4x over x s plus 1 dx. Great. Now let's just split this integral, and we obtain what? First of all, this is the sum of two integrals, and and for this part, one x simply cancels. So we rewrite it precisely like this. As b the integral from b plus infinity dx divided by x to the power of s um, minus s, the integral from b to plus infinity for 4 of x divided by x to the power s plus 1 dx. So here nothing special. We shall just use the for the first term. We shall just use the Newton-Leibniz formula, and we know how to compute the integral of power function, and we obtain something like this. So we obtain s divided by so the upper term is the upper term is 0 in infinity, and in the lower term it should be taken with a minus sign. So we write it precisely like this. So it would be s divided by 1 minus s. Here we do not forget minus, and b to the power 1 minus s. Cool. So what shall we do with this guy? It is reasonable to split it to the intervals of the length 1, just to make this floor function more defined, and to reduce the problem to the one known integrals. So we do the following: minus s, bring s here. So uh, and goes from b to infinity of the integral from m to n plus 1 m x to the power of s dx. Right, we just do the standard computation and compute this integral. So we bring this term without any changing. And here we obtain what? Of course, this minus s cancels by the this s cancels with 1 divided by minus s, which we obtain from integrating the power function. So it becomes plus and something like this, and from b to infinity of n divided by n plus 1 to the power of s minus n divided by n to the power of s. So great. And let us now look at this guy. This guy here, in fact, we can notice that this guy is kind of telescoping. It's kind of telescoping series. So why? Here at the previous step, we add n terms of the kind n plus 1 to the power of s. But for the next term, we will subtract n plus 1 of those terms, which leaves us with the following. So we just bring it right here, and um, uh, and we pull out the first term. So we are left with b to the power 1 minus s, and minus the series which we actually want, b plus 1 to infinity of 1 divided by n to the power of s. So what can we say about this guy right here? By bringing it to the common denominator, we can actually obtain that it is nothing but b to the power 1 minus s, 1 minus s with a minus sign. So right now we are ready. So we just substituted right here. This part, as it goes with the minus sign, completes our series for Riemann zeta-function. And this guy right here is subtracted from this guy right here. So we've got our series for Riemann zeta-function, and thus the fact that it generates the analytical continuation of Riemann zeta-function is complete. So now let us just prove another one intermediate step. So let us proceed. So before we make things fun, let us prove this small intermediate step. It may seem obvious, but still. So how would we do that? We actually do the usual trick for working with the difference of two square roots. So we just multiply and divide it by the sum of those square roots to complete the perfect square. So what we obtain? We obtain the following. We obtain that it is limit as x goes to infinity of x squared minus the floor of x squared divided by the square root of x squared plus the square root of the floor x squared. So that's nice. So what can we observe here? Then we observe that this guy is actually bounded by 1, just by the definition of the floor function, by the definition of integer part of the number. So as it is bounded by 1, and of course, since here x is positive, it is greater or equal than 0. So what we obtained? We obtained something bounded divided by something that goes to infinity, which most definitely goes to 0. And everything is alright. So now we are ready to the funniest part. So let us get to the deriving of our desired identity. Actually, we use the formula which we have proven before to express zeta of one half for arbitrary k just being big enough to make k plus x positive. So now we can actually notice that those integrals, those massive integrals, were just the remainders of absolutely convergent integrals. Thus, they converge to 0 as k goes to infinity. So what shall we basically do? We just equalize those guys and send k to infinity. So what shall we obtain? We obtain that limit as k goes to infinity of the difference and from 1 to k plus x squared or 1 to 1 divided by square root of n minus the same sum but to k squared of 1 divided by square root of n. And it equals so 1 minus 1 half is simply 1 half. And after division by 1 half, we obtain that it is nothing but 2. So we obtain that it is 2 limits as k goes to infinity of the square root of k plus x squared florid minus the square root of k squared. So what we shall do now? Let's add and subtract this guy, but without the floor function. As you may see, those limits exist separately. Thus, we can just split them. So we obtain that it is nothing but to limit as k goes to infinity of the square root of k plus x squared minus the square root of k plus x squared. And here we've subtracted this guy, and here we add this guy. Two limits as k goes to infinity of k plus x squared minus the square root of k squared. Nice. And now what we can say? We can say that this guy by the previous step is simply 0. So it is 0. And now we are left with this guy. But we just use the definition of the square root. And we just compute the square root of the square number. And we obtain that it is being nothing but 2 limit as k goes to infinity of k plus x minus k. Here case cancel out, and we are left with lambda just to x. And thus our statement is proven. So I don't know. It may be quite useless, but still beautiful identity. At least, you see, it's. I consider this to be beautiful, as even after taking the floor function of those, we still obtain the complete information of X. I don't know why, but it fascinates me. So I hoped you enjoyed it too. If so, please don't forget to like and subscribe. And if you didn't like, please dislike and unsubscribe. But for now, it's all. Well, for now, it is all. And the only thing I want to ask you is to remember that the best is yet to come. Thanks for watching.